And likewise for the quarks, you could say quarks have substructure, and if you bang them hard enough, you could excite them into higher particles. And that could just be a manifestation of the binding energy, just like the binding energy of the nucleus. There could be this new force that binds together the particles into the ones that we know about, but once we hit them hard enough, we can break them apart into what they're made of. But we've tried, and we haven't seen any substructure yet in electrons or muons.
Hyperdimensional is that in order for them to be accessible at the LHC, there must be extra dimensions. Remember, extra dimensions explain why gravity is weak. It's one possible explanation for why gravity is weak. So in these theories, gravity is actually not that weak. If you look at gravity at very short distances, at subnuclear distances, at distances that LHC will probe, gravity is not intrinsically weak. It only gets weak if you look at it from far away, from large distance away. So because gravity is not intrinsically weak in these theories, you can actually see effects of gravity, such as black holes, at the LHC. So that's why having extra dimensions that are large is crucial to producing black holes at the LHC.
We know black holes exist. They're not just theoretical. We can see them in space. Big black holes with masses of many, many times the mass of our sun. In fact, at the center of our own galaxy, there's a black hole. You can see stars orbiting this black hole. They think it's around several times 10 to the 6th, several million times the mass of our sun. But the kind of black holes that we're talking about at the LHC are really, really very different. We know that if you get enough matter, enough mass energy density into a small enough place, a black hole has to form, right? And so there's the notion that we could do this because we're going to a new energy frontier at the Large Hadron Collider. If there's enough energy, we could create a black hole. But this wouldn't be a conventional black hole that exists in our three-dimensional, three-space, one-time dimensional world, 3 + 1 dimensional world. It would have to be a black hole in higher dimensions, and the reasons for that are mathematical, but you would have to have extra dimensions to create black holes, to allow black holes to be created at the Large Hadron Collider. And as Stephen Hawking has predicted, any tiny black hole like that would decay very rapidly, and we call it evaporate. That's a good analogy, but it's not really evaporation. It's just disappearing, basically, back into energy form. It wouldn't, wouldn't sit there and grow.